Hello, it's Keith here, and this is lesson 2 of the simple series of my 8086 assembly programming tutorials. Today we're going to be looking at a very simple example for the Wonderswan. It's very much like the last one we did, and we're going to create a smiley, a single bitmap on the screen, a tile in this case, it's a single tile. We're going to move it around the screen with the controls of the Wonderswan. So this is going to actually compile on two systems, the Wonderswan black and white and the Wonderswan color, because there isn't a whole lot of difference. It's just the definition of the tile that's different. So here you can see we've got our smiley. It can move around the screen one tile at a time, and it can't go off the screen because we've got some boundary checking going on. So there we go. So that's the Wonderswan black and white. Here's the Wonderswan color version. Basically exactly the same because virtually none of the code's any different. And that's what we're going to be doing today. Should be quite interesting. Let's go over to the source code and let's take a look. Okay, so here is our example here. Now the first thing we'll discuss is the sprite itself. So the sprite you can see down here at the bottom in this bitmap test section. Now there's two versions because the system is actually different. We're using the full 16 color mode on the Wonderswan color here, and so you can see there are 4 bit planes here for the 16 colors. So there's 8 lines. Our smiley is 8 by 8, so single tile. You can see it just here. And so in Wonderswan color mode, we need 4 bytes per line here. In the black and white mode, we just need 2 because it's a 4 color system on the black and white system. So we've got our 2 versions of the sprite there. Now they're included as text data, as DB statements here, but I actually created the file with my free AccuSprite editor. It's free and open source. If you go to 8086 here, Wonderswan, and you can save 4-bit and 2-bit planar, which is the correct format for today's example. The Wonderswan also supports linear formats, so you've got a choice of bit planes or normal data, if you would call the other one normal. I'm not sure what you would call the other one. I tend to call it linear, but I don't think that's a standard name. I got that from the Atari links. That's what that called, that format. Anyway, so we're going to look at the code, and there's not too many changes between the Wonderswan color and the regular Wonderswan. So first of all, we've got our program start here. We're defining our code as being at segment F000, and our data is at quadruple 0 here. That's the RAM segment. Now the program start label here is needed for the end of the program. Ironically, we've got a footer defining our cartridge format here. So we've got this at triple F0 here, and we've got a jump to the start of our program here, and a few standard things you don't want to change. Now our program starts here by defining a valid stack pointer here, otherwise we won't be able to call anything and we will have quite a bad day. And then what we're doing here is we are starting by setting up our screen here. So we've got a lot of standard settings that we're sending. Basically though, what we're doing here on the Wonderswan color is we're defining a 4-bit per pixel 16 color screen here, and we're setting planar graphics here, which means bit planes. On the Wonderswan Classic, we are just defining the bit planes here. We can't have 4 bits per pixel, but we want that set up that way. And then we are outing that to port 60, which selects the screen mode. And then we're just resetting the scrolling position of the tile map here, so we're zeroing that. And then what we're doing next is we're defining the screen base here. We're setting up the screen base for our tile map here, and then we are turning the screen on here. And on the Wonderswan color, we're also setting the color brightness here, although I don't think that does very much, at least on our emulator. Now what we're doing next is we're setting up the colors. This is of course very different depending on if we're using the Wonderswan color or the Wonderswan black and white. We have a special palette here in our RAM, and to set this up we need to write to memory address FE00 and onwards. So we are just moving those from our defined palette to the palette RAM on the Wonderswan color. Now the palette format you can see all the way down here. So we've got 1 nibble per channel, which is a very sensible format, and the top nibble is unused, and then we've got 1 nibble for red, green and blue here. So these are our colors. So this is a dark blue here, this is a yellow, and so on. A very easy format to work with on the color system. Now this was added in the color system. The black and white system doesn't use that. It uses something totally different. What we do on the black and white system is we define 8 colors with these ports here, and so with 1 nibble per color, and this is a sort of grayscale brightness, and then from those grayscale brightnesses, those 8, we then select 4 for our palette, and that's what we're doing here. So basically here we're selecting a I'm not quite sure why we have 8 and then select only 4, because 4 would really be quite adequate. But anyway, so we've got our smiley here on our black background, but if we prefer, we can invert that very easily with this example just by doing this. And now we've selected the opposite colors. So yeah, we need to select a series of gray shades and then select 4 of those 8 to make our palette here. And that's what we're doing here. We're selecting palette 0, which is the one where our example is going to use. You can have multiple palettes, I suppose, so there is some logic to those 8 shades of grey. What we're doing here is we're just clearing the tile map. Now actually the tile map would be empty on startup anyway, but for completeness we're just wiping it all out. The tile map starts at memory address 1000 in hexadecimal, and the tile map is 32 by 32. The visible screen isn't, it's slightly larger. We'll just discuss that in a moment. Now what we're doing next is we're transferring that bitmap to video memory. Now on the Wonderswan black and white, we need to move to memory address 2000 in RAM. On the Wonderswan color, we need to move to memory address 4000, so depending on the resolution, whether it's 2-bit planes or 4-bit planes. Now what we're doing here is we're actually defining our smiley as tile number 128. So we've loaded AX with the tile number we want to write to, and then what we're doing here is we're multiplying that up according to the number of bit planes on our Wonderswan color or our Wonderswan black and white. So it's 2-bit planes on our black and white system, 4-bit planes on our color system, and so 16 bytes per tile on our black and white or 32 bytes per tile on our color system. So that's calculating our destination in RAM, and then we're just doing a repeated transfer from our source data, which is our bitmap file, and we're calculating the size here in CX. Bitmap test end is the end of our bitmap data. And so this is our bitmap data, and we've calculated in CX the number of bytes we have to transfer, and so our rep move SB here is transferring all of those bytes into the video memory there. Okay, so that's how we, it's quite a lot of it, but this is how we set up our screen here. We've got our colors set up, we've got our tile map cleared and defined up here, and we've now got our single tile for our smiley. Now let's actually have a look at how we show the tile to the screen. We've also already had a clue. The tile map is at memory address 1000 and it's 32 tiles wide. Now the other thing we need to know is that there are 2 bytes that define each tile. You can see here the tile number is defined by these bits T here. We've got 4 bits for our palette, and we've got some options for flipping and a Wonderswan bank. So basically each tile is 2 bytes and each line is 32 tiles. So to calculate an XY position into a memory address, what we do is we take our X position times 2 plus our Y position times 64, because 32 times 2, plus our screen base, which is at memory address 1000, and that converts an XY position into a destination for our tile number, and that's what we've done here. We've calculated that destination here, and then we have moved our AX, which is our tile number, to that memory address here as a word, because it's 2 bytes per tile in that definition. And so what we're doing if we want to show the smiley is we select the tile 128, where we loaded that smiley in, and we show that. And if we want to clear the smiley, we're using tile 0, which is empty. We're assuming it's going to be empty at least. So we've got 2 versions here: show sprite to show the tile and clear sprite to clear the tile. Now they're not technically sprites. I'm using the word sprite because it's consistent with my other examples where we're using software sprites in some cases. Okay, so that's how we show our sprite. So at the start here, we're loading DH with our X position and DL with our Y position here, and we're running show sprite, which will show that tile to the position. What we want to do next is we want to process the key presses and see if any keys have been pressed. Now on the Wonderswan, we use port B5 to do this. The top 4 bits, or at least bits 4 to 6 here, we'll select which part of the keypad we are reading. So there's 2 direction pads and there's some buttons, and so depending on which of these bits we set when we read back, the bottom 4 bits will select one of those and return the state of the directions. And so we are going to use the X pad in this case, and so we need this bit set. We then write to port B5, and when we read from B5, we will get the 4 directions in the bottom 4 bits here. So we're masking those here because the other bits won't provide anything useful. And if that is 0, then no keys have been pressed yet, so we're just waiting until they have been pressed. once they are pressed, we need to remove the old sprite from the screen before we change the position. So we're running the clear sprite function here, which will remove the old sprite. And then what we're doing next is we're testing each of the directions one at a time. So this is the up direction, this is the down direction, this is the left direction, and this is the right direction. And what we're doing is we're seeing if that key has been pressed, and if it's not, then we're skipping over the rest of the code for that direction. In this case, if we get to here, then up has been pressed. And what we need to do next is check if the position of the smiley is already at the limit at the top of the screen, which is 0. So we're comparing to 0, and if we're at 0, we can't move up anymore, and we're skipping over the next command. The next command here is decreasing DL, which is moving the smiley up the screen, you see. So that's going to move us up the screen. What we're doing next is we're checking the down direction, and if down is not pressed, we skip over here. If down is pressed, we're comparing to the limit of the bottom of the screen. The screen is 18 tiles tall, visible screen, so we're checking 17, 0 to 17, and if we're already at the limit, we are skipping over, but if we're not, then we can move down the screen. And the same for left here, and the same for right here. The screen is 28 tiles wide. Nice big screen on the Wonderswan. Very nice system. It's a shame it didn't do better. But anyway, so we're checking the 4 directions and moving our sprite accordingly. Once we've moved our sprite, we show the new position of the sprite, and then all we've got here is a delay. It's a very crude delay to slow the game down because the Wonderswan is very fast. And then we're looping back up to here for the next move. And that's how we get our smiley to the screen and move it around the screen on Wonderswan Classic and Wonderswan Color. Now, of course, if you wanted to have more graphics than just one sprite, which I'm sure you would, all you need to do is create some more bitmaps, put them in that bitmap section, and this will automatically load them in from 128 onwards. And the reason we're using 128 onwards is the Hello World example loaded our font into characters 0 to 96. So these are out the way of our font. That's why we're starting from 128. So you could combine these together to give you a font and give you bitmap graphics. And as I say, you can load in more bitmap graphics just in this area here, just before bitmap test end, and you'll have a 129, a 130, and so on. And that's what you would do to create a game. So there we go. As I said, you can go to my website and download today's example, and I hope you can make something useful out of it, because if you can, then best of luck to you. Or you can also, of course, download the build scripts that I use to create this, and also the pre-configured emulators, hopefully. So you should be able to get everything going as quickly as possible, because I want you to have some fun with this. As I say, Wonderswan, while it wasn't a big success in terms of its sales, and I don't think it made it to the West at all, if you're looking to do some 8086 programming, it's a fascinating system, and it's pretty easy to get started with, so it's definitely worth you having a look at. Anyway, if you've liked what you've seen today, hit the like button and hit subscribe. If you like the videos, YouTube recommends them, and if you subscribe, it lets me know that it's worth me keep making them, because it's a lot of work to keep researching these, writing the documentation, and recording the videos, so that would help me out a lot. Anyway, I hope you've enjoyed this. Thanks for watching today. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.